has like 1 bar on the battery right now. Of course it does. Where's this even go?
See how far we can get.
All right, everybody, let's get started. We're gonna finish up talking about electron configurations in the lab. We'll get as much of the lab done as you can today, but whatever you don't finish, you can finish at home. All right, so we did this. This is where we ended off in lecture, getting the number of electrons, neutrons, and protons, given an elemental symbol. Here, in the next example, we have different arbitrary elements, right? So X, Y, Z, and R just represent any compounds here, and you're asked which of the following are isotopes of each other. So what was an isotope again? Something's equal. What's equal? Electrons and protons, right? So isotopes have the same number of protons, right? But different what? Mass number. They can have different electrons actually because you can have ions and stuff that are going to be charged, but it's the same mass number, right? So which of these are going to be isotopes of each other?
Y and R.
Y and R, right? Because if we look at them, they have differing mass numbers, right? So these are different.
Different mass, same electrons.
And the same protons, right? Because the atomic number, same Z or proton. Sam?
I'm a little confused. What exactly is the mass number?
The mass number is the mass of the protons and the neutrons combined. So a mass number is equal to number or mass of neutrons plus Z, the atomic number, which is the number of protons.
Sorry, Professor, say that one more time.
It's the number of neutrons plus the atomic number, and the atomic number gives the element its identity, which is the number of protons. Right, so any two elements, they have the same number of protons, it's the same element. Right? They can have different number of electrons, that makes them ions of each other. They can have different number of neutrons, that makes them isotopes of each other. But the protons give the element its identity. So this, in this case, Y and R here, those are, just random, but hydrogen will always have 1 proton, for example. Helium will always have 2 protons, for example. X and Z, for example, those have different mass numbers and different number of protons, so those can't be isotopes. X and Y have the same mass number, but they have different atomic numbers, which means they have different protons, so they are not isotopes. All right, any questions on that? Karen?
What are the top and bottom numbers?
All right, so the way it worked was if this is our symbol, we have A and Z. This was our atomic number, and this was our mass number. And this is in this notation when we're writing it like this. If you look at the periodic table, it looks like Z usually, whatever the element is, and then A is down here.
But typically, for the problems you'll give us, it'll be the first example.
It depends if I'm talking about isotopes and stuff. This is generally how they're written in terms of isotopes, but we're going to be comfortable using the periodic table for almost everything else in the class. And one way you can kind of just rationalize it, right, is the mass number is usually always going to be bigger than the atomic number because the protons and the neutrons will always have more. It'll be a larger number than just the protons itself, right? The only way those two are the same is if there's 0 neutrons, which would just be neutral hydrogen. All right. Okay, so here we have another kind of qualitative question. So we said we have this table here of information. What's the most abundant isotope of boron, right? Abundant was related to the actual mass that you get versus the 2 different isotopes that we have in the universe that exist, right? So here we have boron 10. and boron 11. That's how you would read those, right? And you say the atomic mass is 10.8, right? So which one of these do you think is going to be the more abundant boron in the universe? It should be 11, right? So how do you know that, Jade?
It's rounded closer to
The value is closer to 11, which means that if we're averaging the amount that's in the universe, right? We add up all the boron and we say this much, right? Add the parts divided by the whole. If we know all the boron, take the parts divided by the whole. If that number is closer to the actual atomic mass, then that's going to be the more abundant isotope in the universe, right? So this is the more abundant, or another way that you can type this would be boron 11 is another way that you can indicate an isotope, is the more abundant isotope because the AMU is closer to that mass number. And when summer?
So the mass number on an element can change?
Yep, because all that gives the element its identity is what?
Protons.
The atomic number, right? The number of protons, right? So you can have differing number of neutrons, but if the protons are the same, then it's the same element.
So you could see a periodic table like that looks different as far as the mass numbers go?
So you usually what's on the periodic table is this value right here, right? So you're given the average mass of all of the boron in the universe.
Oh, okay.
That's always going to be there. But you know, boron maybe has 5 different isotopes. And so based off of this mass, you know, we average it over all the different types of boron there are, because there's boron with, you know, 5 neutrons, boron with 6 neutrons, 7, so on and so forth, right? So we just look at the average atomic mass, and that's related to which isotope is the most abundant in the universe.
Okay.
Good question. And so once you get to like more than 2 isotopes, it's a little harder to determine, right? If you have something in between these two, then you're like, well, it could be, you know, somewhere in between. It's hard to say what the most abundant is. The other way that you'd be able to do something like this is if you were given the relative abundance of that material, the atomic mass, or the AMU of that specific isotope, right? So does anyone know what Ag is?
Gold or?
Close. It's silver, right? So AU is gold and Ag is silver. Right? So we have 2 different isotopes. We have silver 107 and silver 109. And you're given the atomic mass of each of these isotopes, the AMU, and the relative abundance of each of these. And if you wanted to find what is the AMU that you see on the periodic table, or average AMU is another way you could phrase that. How would we do that given these values, right? So if we're taking an average of something, given the percentages, does anyone know how we use those values with each other?
You can add it and divide by 2.
If you add them and divide by 2, but when you're doing that, what you're doing is you're giving equal weight to both of them, right? If you just add 2 things and divide by 2, you're saying this is 50% abundant and this is 50% abundant. Why? Because 1/2 is 0.15. But here you're actually given the relative abundances of each of those. And so what Sam just said mathematically, the way we would write that, if they were equal weight, meaning 50-50, then we would say the average is equal to AMU, or isotope 1, so the mass of Ag107 times 1/2 plus the mass of Ag109 times 1/2. Right? And so intuitively we know if we add a bunch of stuff together and divide by the total number of things, that gives us an average in some way. But what that's assuming is that each of these averages have the same, or each of these values have the same weight, meaning they occur just as much as the other ones. So the way we account for something, if we have different weights, right? Weights or percentages associated with those values. Does anybody have any idea how we might incorporate these values into an equation like this? Sam?
You could multiply, like, at the bottom, you multiply by 1/2, you could multiply by like 0.51.
Yeah, so you just, instead of having 1/2 for each of these, and sorry, I know that it's low for some of you guys, instead of multiplying by 1/2, which is just 0.5 for each of these, you would just multiply by the actual decimal value of that percentage. Right, so what that would look like, is it okay if I go to the next slide? Is anyone still looking at this? I'll give you a second if you're, I know a second. What that's gonna look like is the mass of AG 107 times the percentage of how abundant it is, so it'd be 0.5184, plus the mass of AG 109 times its abundance, 0.4816. And so what that looks like for, and what we would say for unequal weights, that would be the average AMU equals the mass of AG 107 times 0.5184 plus the mass of silver 109, 0.482 or 16. Did I do that right? Yeah. Alright, so all I did is I just replaced the 1/2s, right, assuming equal weights with the actual weights of those things. So for something like this, you would have to be given the abundance of that material, of whatever isotope that is. So that would be, if I go back and plug in values, 106.91 AMU 0.5184 plus 108.90, 108.90, 0.4816. Times 0.5184 plus 108.90 times 0.4816. So you get about 107.87 AMU. Oops.
What does that say under
AMU. Yeah, that's just saying the atomic mass of what naturally occurring silver would be, right? Because we're averaging over all the different isotopes that we can have for silver. Vanessa? Oh, I got those values from right. So the table would give me some value like that. What the relative mass of each isotope is.
So those would be given.
Yeah, those would be given for something like this. Yeah. All right, and this is just a good kind of segue into, because as we do more calculations, calculating averages from percentage, right? Something that's useful in science in general. This one. Any questions on that?
We wouldn't round?
This one you wouldn't round necessarily because you have, the accuracy of adding in 4 sig figs, or I guess you would round it to the 10th place right there. I wouldn't worry about it for this one, but this one you would actually round to the 0.8 right there. Because you get 4 sig figs, so 4 sig figs, that would round both of them to the first decimal place, so then your answer has to have one decimal place, is how it would, the adding and subtracting would be there. I'll write that. So this would be 107.9 AMU with sig figs. Okay. Alright, so this gives us an idea of how the masses of isotopes, a little bit of the structure of the nucleus of the atoms, right? We have protons and neutrons that both have the mass. They hold all of the mass of the atom, right? So the electrons do have mass. The only thing is an electron has about 1/1000 or 1/2000 the mass of a proton or a neutron, right? So the electrons contribute very, very little to the actual mass of the atoms. And so that leads us into then, so we're talking about the nucleus here, and that's what isotopes and nuclear chemistry deal with. That leads us into the modern version of the quantum mechanical structure of the atom, right? So this is called the Bohr model of the atom, which is even today still used to kind of give a qualitative description of what the atom itself looks like. And so this looks at the importance of the arrangement of electrons around the nucleus, right? So now we're really kind of connecting how is the periodic table going to be organized to the structure individually of atoms themselves. And so what is model suggested is that the atom consisted of electrons that are orbiting, right? So they're circling the nucleus, and they're at specified distances, and these were related to the energy levels of that electron. Say, well, what does that mean, the energy levels? And so what Bohr's model kind of introduced or brought into question was related to something that Einstein won a Nobel Prize for, which was the photoelectric effect. And that's that these electrons can only exist at very specific distances from the nucleus, meaning that this electron here could exist in this orbit or this one, but it would not exist in the space between these two. Right? So this is kind of the idea that came from quantum mechanics, that things don't act in terms of a continuous model anymore, right? So if we think of, for example, water flowing, you think of water as a continuous medium, right? It's connected to each other, it's not broken up into little pieces. What quantum mechanics says is that, well, that's not how things behave anymore. Once you get really small, things act as discrete, act in discrete ways, right? So a quanta means just a single package or something, right? A quanta, that's where quantum mechanics come from. And it's saying that the energy levels of the electrons, which is related to how they move around the nucleus, are quantized, is what we would say. We would say the orbits are quantized, meaning that we can't exist in the spaces in between, but only at very specific orbits around the nucleus, right? So this is where, you know, kind of physics really starts to get funky because, well, what restricts it from interacting in that way, right? And that has to do with another physicist or equation that we'll get to in a little bit. And so how these energy levels are filled, they're going to be basically filled from the lowest energy to the highest energy. The lowest energy is called the ground state. And the higher energy levels are called excited states. And so the same way we talked about potential energy, things tend to move towards lower potential energy to keep everything nice and happy. They move to lower energies. The same idea is in quantum mechanics, except now you're only existing at very specific orbits around the nucleus. And the only way that we can move between these energy levels is by existing or absorbing or releasing energy that's equal to the energy difference between these levels, right? So you can only move between them by absorbing energy, right? So if we hit it with something like light, which is one way that we can absorb energy, right? You hit something with light, it can heat up. That electron can then move to the next energy level, and it takes in that energy to move to the excited state. If an electron was to then move down in energy level, the only way it can do that is by emitting something like light.
So it needs an outside force.
It needs an outside interaction to be able to move between energy levels. Generally, if you exist in a high energy level, this process, relaxing back down, the same way a ball rolls down a hill, will happen spontaneously, right? You're saying, I'm at a high energy level and I want to move back down, but when it happens, it has to release that energy in the form of light, usually. There are other pathways, but that's beyond the scope of this class on how that happens.
So if it's ground state, it is light.
Mm-hmm. And then once you're at the ground state, you can't go any lower in energy.
Okay.
So the ground state is the absolute minimum of energy. So this is when we talked about temperature and stuff. Well, it was the advent of quantum mechanics that said there is no absolute zero, because there's some ground state energy that you can't go below, right? You exist even in the vacuum of space. There's just energy
So
floating
how do
around.
you calculate if it's in the ground state or excited?
So that falls out of the equation that we'll talk about in a little bit, right? So there's a guy named Erwin Schrödinger who developed an equation, and so the reason that quantum mechanics and all of this is so funky is because there's not like an intuitive way to interpret things. It falls out of this hypothesis that, okay, Bohr said that there's going to be discrete energy levels that things exist at. Another physicist developed a way to test that. He developed an equation, okay, let's assume that and see what happens. And so he did that and said, okay, well then, if you assume that, we get these different energy levels for atoms, and they exist in there. And so that's kind of how it came about. And then you find testing these things that is actually how things behave, right? So it's a very foreign, non-intuitive way. So this, you guys may, have heard that the universe is not deterministic in a way, and that's because of people's interpretation of quantum mechanics, meaning that things, right? If something like light interacting causes things to move from one state to another, then that means that anytime you interact with a system, you're interfering with it somehow, and then whatever the state it was in before, you can't directly observe anymore. So we can talk about that, during office hours if you want to talk about philosophy of quantum mechanics and stuff. It's not necessary for this class, but things should feel a little uncomfortable with this idea that things are no longer continuous, and they, behave according to something that was just an equation based off of this hypothesis. Okay, so what is this Bohr? What do we leave with the Bohr model of the atom? Is that when excited electrons return to the ground state, they release energy in the form of light. But the Bohr's model still left some questions about, right? So Maxwell, who was 100 years before this, I mentioned him in lecture as well. He said that if you have a charge and it's moving in a circular motion like this, or it's accelerating in one way, that charge will emit light. And it's true, if you start to create orbiting electron or something like that, it will start to release light just based off of a classical phenomenon. We're not even thinking about quantum mechanics at that point. And actually, when we get solar rays from the sun, they'll ionize some particles in the atmosphere, they'll follow the magnetic fields, and they'll release light, and you can see something kind of like the northern lights in that case. So Bohr's model has these things circling the nucleus. So if they're circling the nucleus, then they should be releasing light and losing energy, and slowly they would spiral into the nucleus, positive meets negative charge, and they would annihilate each other. So there's something else funny going on here that isn't explained by Bohr's model of the atom. So that was the problem of decaying orbits. And then there was also an issue with very large atoms with lots of electrons. The behavior wasn't very well explained, and that was something that wasn't until much later was actually dealt with. And so how was this resolved? Well, in 1926, so about 20 years later, Erwin Schrödinger came along, and he developed what was called the quantum mechanical model. And what he did is he said, okay, well, let's assume that, electrons don't actually behave like individual particles. Instead, they're gonna act like waves, right? So he developed a wave equation for the energies of electrons in a nucleus in terms of the Schrodinger equation. And so you don't have to know this, but this is what the Schrodinger equation looks like. It looks something like that. We have some, H and En can have very complicated terms in there, but this is the simplified version of what the Schrodinger equation looks like. And what it says is, well, we treat the electron like a wave, right? And we solve this equation, we're going to get discrete energy levels, right? But instead of an orbiting electron that's moving like this, we have standing waves. And what standing wave is if you think about jump rope, right? A jump rope is a standing wave, right? It's a wave that's moving up and down, but it's just staying in place, right? It's not like a wave in the ocean that's propagating away, right? And so, if you spin a jump rope really fast, what happens? Like you just one person holds it still and the other person spins it really fast. Has anyone done that before? A jump rope? Do people still play jump rope? Yeah, kids, right? If you spin it fast enough, eventually you won't just get one kind of thing moving. You'll get halfway through, there's a spot that's staying still, and you get two parts of the jump rope that are moving, right? And if you go even faster, you can get three, right? Does that ring a bell for anyone? Right? If you really try to spin it really fast, you can get multiple parts going up and down, and multiple what we call nodes, where the jump rope pretty much stays stationary in the sense that it's not moving up and down. It's like the wave is going through those points, but those points themselves never move. So what I mean is it looks something like, this is a normal jump rope, right, going up and down, that's what's moving. Then you can, if you do it really fast, you can have something that looks like, that's a terrible drawing, but something like that, and then even faster, it'll look something like that, right? So those points right there are staying still. Those are what we call nodes. Those are what we call a standing wave. And so what Erwin Schrödinger did was he took this idea and applied it to, well, if an electron behaves like a wave, and we solve this equation, these electrons really exist in what we call probability standing waves, right? So they don't exist as a particle anymore, but they are now a probability of existing at a certain spot in a standing wave around the nucleus, right? So that means we don't have to deal with electrons orbiting into the nucleus and decaying anymore, because they just exist as a wave that's kind of moving up and down. And how do we interpret what that wave means? Well, that wave, right, that's going up and down, that height of however it's displaced can be represented as the probability of the electron existing there, which should be really, really kind of foreign concept for us to think about, right? So it doesn't actually exist in any one spot until you interact with it, right? So what we say is that the electron exists everywhere around the nucleus until we hit it with some light, and then what it does is it collapses what we call the wave function, or the probability. It collapses it into a spot, and now the electron is a particle that exists in one spot. But up until we interact with it, it exists as this probability. And you might say, well, that sounds...
And it's constantly moving.
It's not that it's constantly moving, it's just it actually exists in a state where it's kind of everywhere at once until you find out where it is. Right, so has anyone heard of the Schrodinger's paradox? Go ahead.
Is it because of the speed?
So it doesn't necessarily have to do with the speed. It's because we're saying the electron is a wave and not a particle anymore. It exists as a wave. And you can actually do experiments where you shoot electrons between two slits, and it will actually make a diffraction pattern on the sensor behind it. So it actually behaves like a wave. And you find as things get smaller, they start to not behave like particles anymore, they start to behave like waves. And so that's what makes quantum mechanics very iffy, right? It's very uncomfortable, because we're saying that the universe is no longer deterministic. If I know exactly where that, electron is now, I've lost a bunch of other information about it.
It's like the double slit theory.
Mm-hmm. Yes, the double slit experiment is what proves that electrons are actually waves, and they behave like waves until you observe them. And so what we say is that electrons exist in this superposition, right? So the Schrodinger's paradox is that, well, you have a trunk and there's a cat in there, and the cat is either alive or dead, right? And until you open the trunk and find out what it is, it's both. right? And that's what we think of the electron. The electron is, well, it's either here or there, but until we observe it, it's in both places at the same time because it's existing as a standing wave around the nucleus. Right, so this, all this is just to say that we solve this equation now, which is a special type of calculus just called a differential equation. So you solve this, and then it pops out that there are a bunch of energy levels that the electron can exist at. So now we're not looking at orbits around the nucleus, but rather the energy of the electron itself. And all that means is just the relative shape or how far that probability density or the probability wave extends from the nucleus. And so there are sublevels, there are principal energy levels that exist within the atom, right? And we can only move between these energy levels now by absorbing light or releasing light. But these are no longer representing orbits around the nucleus, but now they represent the actual, this probability wave and the energy of this probability wave of the electron, right? And so this energy level, this principal energy level, is designated by this letter N, right? And so N is one of a number of quantum numbers. Right, and what this number N describes is just what energy level the electron is at. And what these energy levels relate to on the periodic table, we'll find, is that these relate to the periods on the periodic table. And these are the principal quantum numbers, right? And so N you can also think of as the electronic quantum number. That's what N is. And there's going to be another quantum number called L, M sub L, and M sub S. And those are all going to have their own quantum number that's associated with it.
How do you get this quantum number?
So you get the quantum number by solving Schrödinger's equation.
Okay.
And so I know we're not solving the equation, we're not going to in this class, but the way you get that is you just go through a very complicated mathematical process of solving this, and just the mathematics spit out these answers.
But we don't even know this.
Yeah, you don't need, we'll talk about the quantum numbers, we'll be familiar with those. We don't need to know how to solve the Schrödinger equation or anything like that.
So will we be provided all of those numbers, the N values?
The N values, we'll talk about how you get those and how that relates to the electron configuration and stuff. Yeah, so we'll talk about that in a second. Right, so this quantum number describes the energy that electron is in. Right, so in Bohr's model, this was the specific orbit you were in, but in the modern model of the atom, the quantum mechanical model, this is just related to that wave that we just solve the math and see what pops out.
And the wave, how do you find the nucleus?
So the nucleus, so in Schrödinger's equation, the nucleus is just modeled as if it was a positive charge. And so Schrödinger's equation is actually complicated enough that you can't solve it exactly for anything other than the hydrogen atom.
Okay.
Right, so the hydrogen atom has one proton and one electron. The nucleus is modeled as just the potential, right? Potential energy of just an electric charge, right? It's a negative charge, positive charge. That was solved 100 years before this. They just plugged that potential into the Schrödinger equation, and that's where these numbers pop out of. But as soon as you go to helium, where there's 2 electrons and 2 protons, it's insoluble. It's mathematically, you cannot solve that equation anymore. There's other ways you can solve it approximately and stuff, and that's how we do the things in actuality. But everything, all this theory is just based off of hydrogen. And you think about how many elements there are on the periodic table, all this theory is just based off of hydrogen alone. Right, so we're extrapolating a lot from this. But from this level of theory, you find a lot of stuff is correct for a lot of atoms. And so within, right, so this is just accounting for the charge on the nucleus. Then you look at other things like, okay, well, how is it, it has, some momentum that's associated with it, you have all these other things. And so these energy levels are then subdivided into sublevels, meaning that within each energy level, you have multiple energy levels. So in the n equals 1 state, right, so this is the n quantum number, the sublevels within each n level, these are associated with the quantum number L, right? And I keep saying quantum number and then a letter right after it, doesn't make a lot of sense. But it's just that quantum number is designated as L. And so within each principal energy level, these sublevels, which I'm going to circle in black, these sublevels exist, right? So these are the sublevels. And what these have to do with, these have to do with the shape of that wave, right? So for the hydrogen atom, it's just a sphere, is what that wave looks like. For once you go up to the next energy level, or the sublevel, now you go into something that looks like an infinity sign and so on. And I'll talk about that in a second. Right, so this sublevel exists at the principal energy level. That's not divided at all. But if we go to now the n equals 2 state, what it looks like is that we have 2 more energy levels here, one for S and one for P. Then we go to the n equals 3 state up here, and now you're going to have 1 for S, 1 for P, and 1 for D. So this is S, P, and then D. Right, so these energy levels get more and more fine as we go higher in energy. Right, and when I say by more fine, it just means that you add more and more sublevels as you increase this n number. And what these things represent is they just represent the shapes of these orbitals. So these sublevels, the shape of the orbitals. And I'll talk about what that means in a second. Of orbitals. Or that's what they're going to be. That's what they're going to be related to. So we have the N.
So everything in the S block would have the same shape of orbitals?
Yep. Everything that's in the S block means the outermost valence shell, and we'll talk about that later, is going to be that spherical S shape.
And same for like E and P.
Yep, that's exactly right. Those are talking about the outermost electrons, but yeah, that's right. All right, so we have these sublevels that then these are, L is called the angular momentum quantum number. And so the same way that N came from modeling the nucleus of the atom in the Hamiltonian, Schrodinger's equation, we put the nucleus of the model, or the atom in there. That's where that N came from. This comes from saying, well, this has to be existing in 3-dimensional space, and we just put the 3D coordinates in there, and that pops out of the equation. And so once you have the M or the L sublevel, those can be divided even further, right? And these are called the orbitals, or these are the specific orbitals within the sublevels. And so for the S sublevel, we're going to have one orbital that can each hold 2 electrons. The p sublevel will have 3 orbitals that can hold 6 electrons. The d sublevel has 5 orbitals that can hold 10 electrons, and F is going to be 7 orbitals that holds 14 electrons.
Why do you have these like numbers?
Because there's going to be rules that are associated with how we have to fill up these energy levels.
And they've like been like calculated way before.
Yeah, so these have all been like determined before, right? So there's certain things that they found out experimentally. Well, when I test this, it doesn't agree with the Schrodinger equation, or they don't agree with the real life doesn't agree with what the equation is telling me, and so they have to then make other assumptions to then get the two things to agree with each other. And so what it is an orbital can hold a maximum of 2 electrons in it. So this is related to the Pauli exclusion principle. Right, so we have a maximum of 2 electrons that exist within an orbital. And each of these orbitals have a specific shape that's associated with them, right? So the D, F, and P and S sublevels have shapes associated with them, and then each of those are further divided within each orbital, right? So the S, so if I draw the shape here, and I'll go up to D because I can't draw an F orbital. An S just looks like a sphere, right? So we think about our model for the hydrogen atom earlier. It's just a sphere surrounding a nucleus, right? That's the electron wave is what's surrounding the nucleus there. A P sublevel looks like an infinity sign. So I'm drawing it in 2D now that these really exist in 3-dimensional space, which means that that's what the probability wave looks like, the standing wave. And a D sublevel looks almost identical, except it's 2 of them combined into one. Right, so as we go up in energy, the shape of these get a little bit more complicated, right, within a single level. But an S level, no matter how many other energy levels exist within inside the atom, the S level is always going to look like a sphere like that. The P will always look like a infinity sign, and so on. F, you can imagine, you get even crazier. It goes off into the diagonals as well. It looks like an octopus. So those are what the shape looks like. And so if we go back to this slide right here, we see that within each sublevel, within each principal level, the same sublevels show up, right? So in the first principal energy level, n equals 1, there's an S level there. That S level looks like a sphere. That's the only one there. Then we go up to the second principal energy level, right? We see that there's also an S level within principal energy level 2. So that one looks like a sphere. It's just extended out a little farther from the nucleus. And then you also have the P level. You go up to principal energy level 3, there's still another S level there because these sublevels exist within each one of these principal levels. And how do we know how many there are? Well, that just depends on the principal energy level. As we get to higher principal energy levels, more sublevels start to exist. All right, so all we have down here, I forgot to write that, is just the S level. It's the only one down there. So it's like you're repeating it every time you go up to a new principal level.
And although the sub-level goes up, it doesn't change?
So the shape still looks the same.
Yeah.
It does change, right? Because when I've gone up to this energy level, right, we think it's higher in energy, it's probably a little farther away. So it's still the same shape. This S is still the same spherical shape. It's just it's probably a little farther out from the nucleus now. It extends out a little farther. And so what this builds is the idea that we have these shells, these energy shells that exist within inside these atoms, right? We have our n equals 1 shell, then we have our n equals 2 shell, and then our n equals 3 shell. And then within each of those shells, we get all of these sublevels that give us the shapes within each of those. So it's like the atom's kind of like an onion, right? So the outermost shells are the highest energy. Then as you peel away the end shells, you have then the sublevels, then you get to the next end shell, the sublevels again, and so on and so forth. And this just keeps going on up until you get to the F sublevel. Once you get past that, then the equation doesn't behave the same way. And so we can relate this structure to then the trends or the properties on the periodic table. And so the electronic structure, which is just the electron structure of the atoms, which is related to the periodic table, this is called the electron configuration of an individual atom. And based off of this hierarchy that we talked about, where we have 2 electrons per orbital, depending on the sublevel gives us a different number of orbitals, and depending on the principal level gives us a different number of sublevels, right? So the hierarchy kind of goes, we have our principal level is greater than our sublevel, and that's greater than our orbitals, right? Within each one is where things get divided, right? So we have our principal, which is the largest scale thing, that gets divided into sublevels, and then those sublevels get divided into individual orbitals. The sublevels and the orbitals are related to the shapes. The principal is related to kind of the overall energy of that level. And then each orbital can be occupied no more than 2 electrons, and each one is going to be with opposite spin, right? So the last quantum number that we didn't mention is called m sub s. And electron spin is a topic that's even more confusing than everything we've talked about so far, right? Because it doesn't have to do with the electron actually spinning, but it's like, well, if we pretended that it was spinning, it would have this property. And they do actually have that property in real life. And what this is just that you can't have electrons with the same property called spin exist inside the same orbital. And that's the m sub s quantum number. And when we draw electron configurations, that just means if we have an up spin, the other one has to have a down spin. Summer?
Is all of this like the Lewis structure or?
So Lewis structure is specifically looking at the valence shell with so it's the outermost electrons in there. So that will be related to this, right? Because how the valence shell fills up, it does obey these rules, but that's going to be a more simplified version of this.
So this is like a broader.
This is a broader kind of looking at the total structure of the electronic structure of the atoms.
Okay.
And so now we've built this kind of idea of what's the structure of the electrons in these atoms. And we say, okay, well, how are we actually going to fill up, right? So, we look at chlorine or something, and that has 18 electrons, right? That's a lot of electrons. How do you fill up these orbitals, sublevels, and energy levels? And again, this spin property is the Pauli exclusion principle. And so actually this quantity, the electron spin, is the most accurate known quantity that we measure. It's like the benchmark. And so how do we fill these things up? Well, the electrons occupy energy from the lowest energy level to the highest energy level, meaning as we're filling up our atoms, we start with the lowest, which is the principal energy level, n equals 1 is the lowest, and then you fill up the sublevels accordingly. And so the energy levels for the sublevels, right, so n goes from 1 to infinity is the principal level. The sublevels, we have S is lower than P is lower than D, which is lower than F for a given principal energy level. And then the orbitals actually all exist at equal energies, but you fill them up a specific way. In that specific way is each orbital on a sublevel must be occupied by a single electron before you can start filling in the second electron. And so that's what Hund's rule says, right? That we fill in empty orbitals in a sublevel before putting two electrons together. And the reason for that is if you're existing in the same orbital, electrons have both negative charge, right? If you get two things with negative charge next to each other, are they happy or unhappy? What do you guys think? Unhappy, right? They're the same charge, they repel each other, right? So it's easy to fill separate orbitals first before you have to start filling in the other ones. And we'll talk about what that actually looks like when we're actually filling in orbitals here in a second. Right, so the main takeaway is we're filling in electrons, lowest energy to highest energy. You fill in the lowest principal energy level first, then you fill in the sublevels according to this order. You fill in S first, then P, then D, then F, and then as you're filling in those sublevels, you fill in each orbital with one electron before you start pairing electrons with each other. And that's what Hund's rule states. And so how do we interpret this, or how do we actually denote this? How do we symbolize this? Well, if this is a given electron configuration, right, this is just one part of an electron configuration, the number 2 here denotes the principal energy level. The letter P denotes the sublevel that we're in. So this is N, this is L, the sublevel. In 6, here denotes the number of electrons in that sublevel. And so this is how we represent an electron configuration, right? This is how the electrons exist inside this orbital. And so this is called what I call them, the letters and numbers notation.
Can I ask a question?
Yeah.
So the number of electrons depend on the sublevel?
The number of electrons depend on the specific atom. And if it's an ion or a neutral atom, right? So if you have chlorine has 17 protons, then you have 17 electrons. And you fill in those 17 electrons based off of this.
Like if F is the massive number of electrons and the sublevel is 14, how would that work?
That means, so if you have an F sublevel, and let's say you have to fill it all the way up, then the maximum that sublevel can have would be the 14 that you're talking about. But if it's the outermost one, it's the outermost shell and it doesn't fill it up, then you have to fill it up partially is how you would fill it up. And that's based off of how much you know you've already put into the atom for all the inside electrons.
Why do we have to do this?
Because this gives us this structure of the electronic structure of the atom. That's going to be related to how things are organized on the periodic table. Right, so today's lab is going to be writing the electron configurations for 4 specific elements. And so this is the letters in notation. This is what's called the orbital notation here, right? So here we also have the principal energy level. Which is N. It's still the number. We have the specific sublevel, which is the quantum number L. And then now the number of electrons in that specific sublevel are the number of arrows. The number of arrows in orbital and sublevel is the number of electrons. Right, so if we were looking at the previous one, this is a simple one because it's just a 1s2 sublevel, right? So there's only 2 electrons that can go in there. So you do 1 upspin electron and 1 downspin electron.
Did you say that the sublevel is represented by the quantum number L? Is
Yep.
that what you said?
Yep, the quantum I know, and I know it's. Did I turn that off? Nice.
I just wanted to make sure I heard.
Oh, I think this died. Oh wait, no, it didn't. Well, wait, yeah, I think it did. Yes, it. But yeah, it was the quantum number L, right? So L just represents the quantum number that you actually get when you solve the Schrodinger equation. Oh, that's a lot quieter. But yeah, that's correct.
So this slide is different from the one you just did?
Yeah, so see here, the number of electrons is denoted by the exponent of the letter P, right? Here, the number of electrons is the number of arrows that are in the orbital itself. So this is called the orbital notation. And so we'll talk about that in a second. All right, let's take like a... Right, so each of these boxes here represents the orbital, right? For the S level, we have 1 orbital, which is why there's 1 box. And it's just labeled the 1s orbital, right? And 2 electrons go in each orbital. That was the slide with all the colorful SP and D things that we did before. Right, so here we have an electron configuration. This is for hydrogen. Hydrogen, we have a 1s1 electron configuration. That tells us that there's going to be 1 electron in this orbital. Right, so we fill in the 1 electron by just putting the upspin like that. Right, so that's the electron configuration in the letters and numbers notation in blue, and then the orbital notation on the left. Right, it says that electron exists. Sam?
When it has 1 electron, will it always be up?
You start with upspin and then you fill in the downspins. You don't you can do it either way. It doesn't really matter, whatever you feel comfortable with. But the convention is usually you do upspins first and then you do the downspins to pair them together. Right. So the electron configuration for that electron, right, is the 1s1 electron configuration. That tells you a lot about the structure of what that orbital looks like for that electron. Helium, on the other hand, right, we have 1 more proton because helium is number 2 on the periodic table, has 2 electrons. So, but they're both still in the s shell, so we say it's the 1s2 electron configurations because now we have 2 electrons that exist within that orbital, right? So we fill in the upspin electron. We have to fill all the orbitals before we can put in the downspin, but there's no other orbitals in an s shell, which means that that goes directly into the same shell, right? So the only way they can exist together is 1 is upspin and 1 is downspin. Right, so they have properties that allow them to exist within the same orbital, right? Normally you'd think electrons would repel each other, but the spin property is what allows them to exist within the same orbital. Right, and this is simple, right? These are the 2 simplest elements that we have on the periodic table, helium and hydrogen. So what about if we go to lithium, which is the 3rd element in the periodic table, right? Well, now we've extended our atom. How? Because we've gone from quantum number n equals 1 to the 2nd period. Remember, the periods are related to the energy levels. So it's quantum n equals 2 now, right? So we first fill in the lowest energy level, which is the n equals 1 s sublevel that has 2 electrons, right? So we fill in 1, and then we have to fill in all the orbitals of this sublevel. There's only 1 orbital, so then we fill in the next electron there. We still have 1 electron left over because we've used 2, and lithium has how many protons? 3, right? Because it's atomic number 3. Which means we have how many total electrons? 3, which means that we've only used 2 so far, so we need to use 1 more. That's going to go in the principal quantum number 2, s sublevel, orbital. So then that becomes an upspin in the 2s1. So that's the electron configuration in the orbital notation. and in the letters and numbers notation. And then if we go again to beryllium now, we fill in the lowest principal energy number. We fill in that all the sublevels for that principal energy number, and then we fill in the next energy level. Right? Do you guys have a question?
No, I'm confused.
Mhm.
I thought S only has one orbital.
Yep.
But how comes two?
Because we're not existing in just this is a different principal energy level. Right? Remember, S is the sublevels within an energy level. Right? So if n equals 1, we have its own s orbital. Then we go to the next principal energy level, which is n equals 2. That's also divided into S, P, D, E, and not for n equals 2, but once we get to higher energy
I
levels.
see.
Yeah.
But because it's in one.
Yep, that's exactly right. So if we're looking at this picture back here, right? This is n equals 1. We fill in the S sublevel, which is the only sublevel that exists in this one. Then we go to n equals 2, and that one has its own S and P sublevels. So I have to fill in both of these before I go to n equals 3. And then that has its own S, P, and D, right? So this is, each principal level has its own set of sublevels. And the number of those depends on actually which one, right? Because n equals 1 only has one S sublevel. It doesn't have a P sublevel. Vanessa?
Wait, so what's the difference between the electron configuration and the orbital?
Oh, the orbital notation. So the orbital notation, we specifically look at the boxes with the electrons drawn as up and down spin, whereas the letters and numbers notation, you just have the principal energy level, the sublevel denoted here, and the total number.
So that one's the electron configuration.
Yeah.
So during the lab, when you ask for the electron configuration, it's like the numbers, and then for the orbital configuration, would be the boxes?
Yeah, exactly right. The orbital notation, so technically they're both the electron configuration, but yeah, that's the boxes is the orbital notation, and if it just says electron configuration, then you're doing just the letters and numbers. Did I answer your question, Laura, too? Right, so we're building it up, right? Right now we're not going to go through all, whatever, however many elements are on there, what is it, 80 something, 90 something? We're not going to go through all 90 elements doing this, but this is how we're building up. As we increase the number of protons, we increase the number of electrons, and that increases the number of energy levels that can exist. Right, so beryllium, we fill in 1s first, all the orbitals, which is only 1, then we fill in the next energy level. We have 2 because we have a total of 4 electrons we need there. So what about if we have something a little bit more complicated than that, right? So let's look at least an example that has the P sublevel in there, right? So we have to get to n equals 2 before we even see the P sublevel. Yep. And P has 3 orbitals within that sublevel. Right? So we fill in, right? So let's look at boron. We have 5 electrons total. We fill in the 1s, because that's the lowest energy. Then we fill in the 2s, because that's the next lowest energy. The s orbitals are easy to fill in, right? Because there's only 1 orbital there. Now we have to worry about the p sublevel and the p orbitals. How many electrons are left over? Right, how many have we used so far? 4, right? And how many does boron have? 5. So we have how many left over? 1, right? And so this one's easy to fill in because then we just put the 1 electron there, and that's what the p sublevel looks like for boron. Right? We just have 1 electron in there. Carbon has 6 electrons, right? So it can bond the most with most other elements. That's why it's used a lot in biology and for making polymers. So that's the same as boron up to this point, right? Because we still fill in. We have 6 electrons total. We still have to fill in the 1s, which is our lowest energy, then the 2s, which is the next lowest energy, and now we have how many electrons left over? 2, right? And then Hund's rule says that we have to fill in things how in the orbitals? 1 electron per orbital before we start pairing them together, right? So we have 1, and then we fill in the next orbital 2. All done? right? So now we have 2 electrons that are unpaired, right? Because they don't have a downspin that exists with it in that orbital. Hund's rule says that we fill in each one like this. And the reason that we do that, right, is there's 2 electrons. Even though they can exist in the same orbital, right? If the house has enough room, you'd rather have your own room, right? So that's why each electron fills in each orbital first before they start pairing with each other. Right? It's energetically unfavorable to pair it before going to the next orbital. Right, so this is what the orbital notation is. And right, and so these blocks for each of these, those represent the entire P sublevel. And these are the 3 orbitals that exist within the P sublevel. That's why we started with just 1 box for each of these. But when we go to P, remember there's 3 orbitals in there, and each one holds 2 electrons. And if you're curious, each one is just, this is Px, Py, and that's Pz. And so let's not worry about nitrogen, because nitrogen is just going to fill in each 3, but let's go to oxygen, right? So we have 4 electrons. And so how is this going to fill up? We're going to have 3 that we fill up. We have 1 left over now. Now we can go back and we start pairing them together, right? And so how do we fill in this one that goes back? You can put it in either one. It doesn't matter because they're all the same. These are all at the same energy. To pair either one, it doesn't matter. But generally you go from left to right. You just fill this because it looks neater in the orbital diagram. And so now we have 2 unpaired electrons and 2 that are paired together in this P sublevel for oxygen. And then you can do this all the way through the group. This one, you'll have only 1 unpaired electron. All right, we fill up each orbital, then we start pairing them. And neon is a noble gas, which means that its valence shell, its most outer shell, is completely filled. And we'll talk about that a little bit later. So that one gets filled, and they're all paired now for neon. Right, and so now we see that 2p6, which is the P sublevel for energy level equals 2 for neon, has 6 electrons in it, right? That's what this is saying. And we have 1, 2, 3, 4, 5, 6 electrons in that sublevel. We still fill things up from lowest to highest. And then how we fill the outermost shell is usually dependent on the specific energy level that we have right there. Right, so that's for P, which only has 3. You can imagine if we extend to the transition metals, which will have the D energy levels, then you have 5 different orbitals that can exist within that. Summer, you have a question?
Yeah, I noticed when you were writing the arrows in 2E, you did 1 in each box, and then you started
Filling them in.
the other ones. Why did you do that?
That's because you have to, that Hund's rule says that you fill in each orbital before you start pairing them together.
And one of them is enough to fill in.
Yes, right. So you put 1 in each before you start putting another one paired with that one. And the reason for that is though, even though they can pair together if they have opposite spins, right? If you had a house, let's say there was 3 of you in a house and you wanted to be in the most content and you had 3 rooms in the house, you guys would each get your own room, right? You wouldn't pair 2 of you in a room and then another one, right? So that it spaces things out nicely. That's why you fill it up that way.
And so these arrows are electrons.
Yeah.
Like, and then those, the exponent numbers should line up with how many arrows, because they're all electrons.
Yeah, exactly. So that's a good point, right? So if you have all of these added together, should be the total number of electrons in the element.
Okay, yeah.
Right, so that's a good way to check to make sure that you're doing the electron configuration right. These exponents should add up to the total number of electrons, which in a neutral atom equal the number of what? Protons, right? So when you add these up in a neutral atom, you should get the atomic number for that element. Now you guys will be given non-neutral atoms, ions and stuff, but for a neutral atom, they should add up to each other.
So this wouldn't apply to an atom that's not neutral?
Yeah, so let's say, if we ionized it or we took an electron away, all that means that is you'd still have the same number of protons, so it's still the same atom, but you would just take away an electron from one of these spots.
Okay.
So it's a good way to make a question a little harder.
Okay.
We'll go through more in the lab. There's specific examples of it. We're not gonna have a whole lot of time to work through the lab, but I just want to go over this. And so this is how we fill things out normally. However, as with most things in chemistry, there are exceptions to filling things out from lowest to highest energy. Right? So nothing's ever as simple as it seems, right? So once you get to the third energy level and above, then you start getting some weird anomalies. What happens is it starts being some crossing between the different energy levels. And I'll give you guys a way to figure it out easily compared to just memorizing it. Right? So the electrons that occupy the third energy level and higher, and these occur in the order of the energy of the orbitals. And so what an anomaly is, for example, is a 3D energy level is going to be higher than the 4s level, right? So the principal number went up, but the energy is still lower than the 3D energy level. And so these anomalies are important because they determine the electron configuration for these specific elements, right? So anything, right? And so if we're looking at the periodic table, as soon as you reach the transition metals, right? If you go down each period, so 1, 2, 3, as soon as you reach period 4, that's when the weird stuff kind of starts to happen. So luckily for carbon, oxygen, nitrogen, you don't have any weird orbitals like that. But the heavier elements, you start to get those. And so, well, how do we deal with this, or how are we going to remedy this? In general, if you write each principal energy level and then the sublevels that exist for that, you can draw arrows that'll tell you how to fill in the electrons, right? So this is, if I said there was one main takeaway for electron configurations to describe to memory, it's this little pyramid that I'm about to draw, right? So the first principal energy level is N equals what? 1, right? And what's the sublevel in N equals 1? S, right? The next principal energy level is 2, right? So we just go there, and that has 2s, and then what's the next sublevel? 2p, right? So we have 2p. Then we do 3s, 3p, and then in the third energy sublevel, we get 3d, and we'll just go up to 4s, 4p, 4d, and then 4f, and that's as high as we need to go to remember this trend. And so the way you're going to fill in electrons, and that makes it so you don't have to remember the anomalies, is you draw arrows that go diagonally here. Oops, let me do a different color. They go diagonally. 3s, 3p, 4d. And this will tell you how to fill in these energy levels. Right, so if we follow the direction of the arrows from head to tail, we first fill in the 1s sublevel. Then we go to the tail of the next arrow, we fill in the 2s. And we saw that already. That seems simple enough. Then we go head to tail, we fill in 2p after 2s. Okay, that's straightforward. And then after 2p, we fill 3s. Then we get to 3p, and this is where the anomaly starts, right? We fill in 3p, but before we fill in the 3d energy sublevel, we fill in the 4s energy sublevel. And then after 4s, we fill in 3d, and then we fill in 4p after that. Right, so this is the anomaly right here that we fill in 4s before we go to we fill in the next principal energy sublevel s before we fill in d. Yep.
Does that mean 3D has more energy than 4S?
Yep, that means that 3d is actually higher in energy than 4s. And there's a diagram on the next one that'll highlight that. You say why? Well, that's just how it works out. That's just the way the world works. Is why 3D has more energy. Most likely because once you get to the D energy levels, you have so many electrons that are going to be crowded together, right? Once you fill it up, that it's going to exist at a higher energy at that point. And if you wrote 5s and then 6s, that would eventually give you the anomaly with the 4f, the F energy sublevel, which you're going to fill in the 5s before you fill in the 6s before you fill in the 4f, right? So with the D, it's easy because it's one less, right? You fill in the 4s before you fill in 3D. With the F sublevel, which I'm not going to explicitly test you guys on, I'm just telling you so you guys have completeness, you're going to fill in the 6s before you fill in 4f, which is a lot. Right, that's 2 quantum numbers, 2 n sublevels away. And so what does that actually look like? Well, actually I don't like this. Where's the... I guess I deleted the other one. Right, so this is another way of just drawing what I just drew, right? You fill in the 1s, you go from head to tail in the arrows, and that tells you the direction that it fills in. I thought I had... Oh yeah, okay, so here's what it... This is what the... Right, as we increase in energy, this is another diagram of looking what that looks like, right? 1s to 2s, it makes sense. 2s is higher in energy than 1s. Then 2p is higher in energy than 2s. Then we go to 3s and so on, right? But this is where the weird stuff happens, right? 4s is lower in energy than 3d, right? And then if we go up here, this is where really the weird stuff starts to happen, right? The 6s is lower in energy than 4f, right? And when I say lower in energy, I'm just looking at how high is it compared to this axis right here. As we go up, the energy goes higher, and we're just filling in from lowest to highest energy, right? So you guys don't have to memorize that, right? I said the one thing that would be good to look at would just be to understand or memorize this, right? Up to 4, and you could even figure it out for F if you had to do this, right? You would just write 5s and then the 6th energy level, and then just draw the arrows, and it would fall out of that naturally. Right, so this is probably the most important thing if you're going to ascribe one thing to memory. It was this, and then how to fill in, orbitals, each orbital individually, and then electrons have to go in the same orbital with opposite spin. All right, so all of this was to give us a relationship to the period on the periodic table, right? So if we look at the periodic table, that corresponds to the number of energy levels that are occupied by that atom, right? So if we look at the periodic table over here, when we think about how we just built those electron configurations, right? We filled in electrons. Every time we go down a period, we went from n equals 1 to n equals 2, right? That means that the principal quantum number here, the highest one is 2. This is going to be 3, 4, 5, 6, and then 7, right? So each period represents the number of principal energy levels within that atom. And then each block, as we go across the groups, is going to end up representing the block or the sublevel that exists in. And so these are called the valence shells. Right? So the period was related to the total number of n quantum numbers. Right? As we go down, we increase the principal energy level. Then as we go across a group, right, then we're filling in the S, the D, and the P energy levels. So we're looking at the outermost electrons. How do they fill? Those are related to the valence electrons or the valence shell. So the groups are related to the valence shell electron structure. And so again, if we were to look at what the electron configurations would look like, right? If we start 1s1 for hydrogen, we go across. This is a noble gas. It's a special noble gas, so we'll talk about that later. This one is 1s2. We go down now to the outermost shell is energy level 2, right? Because that's what period it's in. It's in period 2. This is period 2, right? So that's why everything here exists, and the valence shell has 2 starting with it. And as we go across, what are we doing? We're filling in the lowest sublevel to the highest sublevel. So the groups are related to the sublevel and the structure of the electrons in that sublevel. Right, so that's why here we see that it goes 2s2, 2p1, 2, 3, 4, 5, 6. As we increase the number of protons, the number of electrons in that valence shell also increase. And that's related to the group number. So nitrogen, for example, is in group 7. This isn't group 7, it's group 5. Yeah, so 5, that's it. I'll write the numbers above here. This is going to be 1, 2, 3, 4, 5, 6, 7, and 8. The outermost shell, when filled, should have 8 electrons. We have 1 here when it's filled, so this only has 1 electron in its outermost shell, so we have 1. Here we have 2. Here we have 2 plus 1 gives us 3. 2 plus 2 gives us 4. 2 plus 3 gives us 5, and so on, all the way to fill out the valence shell, right? So periods are related to the principal quantum number, and groups are related to the valence shell, or the outermost shell of that sublevel for the atom. And what we find is this shell, the configuration of this valence shell, is what determines the chemistry of that atom, right? That's why carbon and silicon have similar chemical properties, right? So people have talked about carbon-based life. Well, what if they do silicon-based life? People have talked about that, you know, follow sci-fi and stuff like that. Well, that's because they have similar chemical properties, because their valence shells have similar shapes and structure, right? Oxygen and sulfur in your body, where oxygen binds, you can usually replace that with sulfur. The halogens are all very reactive because of their valence shell. And then the noble gases are all very not reactive because they all have a full valence shell. Okay, so we'll continue this lecture on Wednesday, and you guys can use the rest of this lab. So we probably won't have enough info to finish all of the lab today, but you can use the rest of today to start working on it, because you'll be able to start doing electron configurations. We'll talk about ions and stuff next time, and a little bit how we relate this to the periodic trends